Here's a pack of traditional incandescent light bulbs. They're rated at 60 watts, 825 lumens. Here's their replacement LEDs. They're also 800-ish lumens, and they're only rated at 9 watts, and they're marketed as a 60 watt replacement. Here's a drill I have. Notice it's marketed as a 6 amp drill. This video is about these terms and others too. And we do use these in our everyday lives because we want our stuff to work right. So we have to get the right ratings for electronic devices and replacement parts. But I think the vocabulary of them often throws people off and makes it really hard to understand what's going on. In this video, I'm going to attempt to define these terms and these units, and hopefully that'll make electric circuits easier for us to understand. The first place we probably ought to start is with how we measure charge. So the standard unit for this is called the coulomb. And an electron is a very small amount of charge. So the coulomb is actually an enormous amount of charge. It's a little bit unfortunate for us because you guys have a good understanding of chemistry and you're used to thinking in terms of electrons. And really we're going to discuss charge transfer as being the movement of electrons. But the electron wasn't discovered till a long time after people started talking about electric charge, and any practical electric charge consists of huge numbers of electrons. So just keep that in mind. It's not just a couple electrons moving, it's many, 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 many. We tend to talk about the energy that individual charges carry through the circuit. And that's why we care about this concept of electric potential that we've hinted at so far. So if you have a volt of potential difference from one end of the circuit to the other, that means that every coulomb of charge that flows will get 1 joule. So voltage is related to energy, but how much energy transfers depends on the number of coulombs of charge that go as well. Another thing that's going to be really important for us is something called electric current, which is called the speed of charge. So I think it would be good for us to look at the other rates that we've looked at so far in this class, and I think that will make electric current make more sense. You have learned 2 rates already in this class. The first one was at the very beginning of the year. We talked about where you are in meters, how fast that changes, meters per second, delta distance over delta time, is velocity. We then learned about energy, and then we talked about power. How fast you change power is also a rate, delta energy over delta time. And that's how we sometimes call power the speed of energy. So we're now going to have to learn about another rate, which is the rate of charge, how fast charge moves. The basic unit for charge is the coulomb. A new concept we're going to learn about called electric current is how fast that charge moves. So you can think of current as being the speed of charge. Just like we had this problem for power being measured in watt, it would be easier to remember if it was joules per second. We'd remember it's a speed. We sort of have the same issue with current. The coulomb per second we named after a guy named Andre Marie Ampere, so we call it the ampere. And most people call it the amp. So if you hear about people talking about amps of electricity, that's how fast charge is moving. And we'll see it's a pretty important concept. So what I'd like to do is look at the different pieces of an electric circuit and to build an electric circuit. And we'll try to see how this new concept of current, the concept of electric potential, and other concepts can be useful for describing what's going on. So I've got my battery, I've got a pair of light bulbs, and I've got some connector wires. And let's try to see how we can release the chemical energy stored in this battery by linking the reaction that produces electrons, the oxidation of zinc, to the reaction that consumes electrons, the reduction of manganese oxide. Now, we need to have some way to get the electrons made here to the other side where they're consumed. And we're going to do that through an electronic device which will use up the energy that's released by those chemical reactions. So I've got 2 light bulbs here. Try not to get hung up on the fact there's 2. this 9 volt, 9 joule per coulomb battery, those charges are carrying enough energy to destroy an individual light bulb. So putting the second one in just means I won't burn it out. We'll go through the physics of that later. Let's see what it takes to make this work. So first things first, I'm going to take the place where electrons are being made, the negative side. I'm going to hook up the black wire, which is the standard color for negative, and I'm going to hook it to one side of my pair of light bulbs. So nothing's happening. Why? Well, there's no pathway back. I guess I could be adding electrons here, but they have no reason to go here because this is already full of electrons, and nothing's being taken out over on this side yet. So if electrons try to go in, they'll find other electrons to repel them, and nothing happens. If we want something to actually take place, we've got to take electrons out of this side by giving them back to the positive side of the battery. So let's do that. We'll hook up the red wire over here, and we'll give that to the positive side, and we're getting our flow of electrons. So I just described to you the situation where electrons leave the negative, flow through a circuit, their energy is taken away by the electronic device. So it's not that the electrons are consumed, it's that their energy is taken off of them and used to do work. And then the now energyless electrons flow into the positive. That is a decent chemical picture of what's going on. However, back when people were first discovering how current flowed, nobody knew what an electron was. So they knew one type of electricity was leaving one end of the battery and going around and coming to the other. And it didn't really matter whether you said positive charge goes from positive to negative, or if you said negative charge goes from negative to positive. They both have the same effect. So when we talk about current, we actually pretend that there are imaginary positive charges that the battery is giving energy to, pumping them up. Those positive charges flow through the circuit and deliver their energy, which is lost to work. We know that zinc is being oxidized to zinc 2+, and manganese oxide is being reduced. And that every coulomb of charge that flows gives 9 joules of energy to light up our light bulbs. But how many coulombs of charge are flowing? And just how many electrons does this represent? Well, to figure that out, we're going to measure the electric current. So I have an ammeter here. And an ammeter measures current, which, as you know, is got the unit amperes, which really means a coulomb per second. So what I'm going to do is wire this ammeter in. We'll figure out how much current's flowing, and then we'll figure out over a period of time how many coulombs that represents, and then how many electrons. So we're going to hook up the ammeter, and it's not very hard to do. We just have to put it in what's called series with the rest of the circuit. Series is pretty easy to understand. It means that as we take our journey from the negative side of the battery back to the positive, that we'll pass through each element one at a time, one after another. Now obviously nothing's happening because the switch is open, but let's close it and observe. So the bulbs light up and the needle on the ammeter moves. And this meter is currently telling us that we have 0.1 amps, 0.1 coulombs per second. So what we're going to do next is we're going to see how many coulombs and how many electrons that represents over a certain time period. Let's count off about 10 seconds. So I'll say go and then stop. So go. Stop. So our ammeter told us we had 0.1 amps, which is the same as 0.1 coulombs per second. And since we waited 10 seconds, that means we got a coulomb of charge. So what does that mean in terms of the number of electrons? Well, since we know the charge on an electron, we can divide a Coulomb by that, and that gives us 6.25 times 10 to the 18th electrons, which out of scientific notation is that number. And I just think that's really cool to look at. I just think that for something as simple as lighting up a bulb, that many particles are doing our bidding for us. So if a potential difference caused by a battery is forcing charge to flow through a circuit and creating a current, which we symbolize with I, is there anything resisting that current? Is there anything that's taking some of the energy away from charges? It turns out there is, and it's called resistance. And that's what we need to talk about next. It turns out that almost all materials, with one exception, a category called superconductors, they don't transmit all of the energy that you put in per charge. Some of that energy is lost in other forms, such as heat. So why is that? Well, I've got a wire here, and let's say I hook my wire up to a battery. Now I've drawn the crystal structure of the copper here, so to remind us that it's made up of atoms. So I think it's pretty clear what's going to happen. Electrons are going to flow out of the negative. They're going to flow into the positive. So there's going to be a pressure for electrons to be going this way through the wire. We'd like to say that that's like a river. They go in just one direction. But it's not really true. What's actually happening is they are going all around. And there's a very small drift speed that means over time, they actually do make it from one side to the other. But all of this moving around, it knocks the copper atoms around, it gives them kinetic energy. And the kinetic energy of atoms is actually what temperature is. So what's happening here is this wire is converting some of the electrical energy that I wanted to go through it. It's converting it to heat. Resistance is the ability of an electronic device to impede the flow of charge. So we could do a number of experiments in class to determine what contributes to resistance. One of the ones I like to start with is with this vintage demonstrator that I found on eBay. It basically consists of 5 coils of wire. There's 10 meters of relatively thick copper, and there's 20 meters of that same wire. There's 10 of thin copper and 20 of that same wire. And then there's 10 meters of the exact same diameter and length as the first coil, but made of a different material, nickel silver. So basically what you do is you compare the different coils of resistance to each other. You measure resistance in a unit called ohms, and we can use a multimeter to do that. And you just put the probes across the two terminals, and it'll give you a value of how much the wire resists the flow of current. Obviously, we're going to compare different coils to each other. For example, to measure the effective length, we might compare this one to this one. To measure the effect of thickness, we might compare this one to this one. To measure the effect of material, we might compare this one to this one. So the things that contribute to resistance, which we give a capital R, the longer the wire is, we expect that to increase resistance. So I'll put an L there for length of wire. The fatter the wire is, you'd expect to decrease resistance because it wouldn't have to be all trying to go through a few atoms. There'd be more atoms for it to go through. So we expect that the fatter we make the wire, the more area would decrease resistance. And then lastly, what type of atom is it? We expect each material is going to behave slightly differently. So there's a factor we call resistivity. It gets the Greek letter rho. And that's just dependent on what material you've got. These three things together contribute how much resistance something has. So all of that was about the natural resistance that happens in wires of different materials. So we absolutely have almost everything we pass current through resisting that current and turning some of the energy into heat. Sometimes we actually deliberately want that to happen, though, and we put what are called resistors. And these are circuit elements that have a certain resistance, We put them deliberately in the circuit. And you'll see us do that as we build our circuits both this week and next week. I'd like to change focus now, and I'd like to talk about power. So power is exactly what it's always been, how fast we use energy. Devices can use energy at different rates, and that makes them work differently. So here's a light bulb that's using energy relatively fast. And here's that same light bulb using the energy much more slowly. Let's talk about why they seem to be so different and how their power usage relates to both their electric potential difference across them and the current flowing through them. So in this unit so far, we've learned about another speed, this new thing called electric current. In other words, the speed of charge. And I'm going to give a hypothesis, and I'll demonstrate in a second, that the power, the speed of energy, is proportional to the current, the speed of charge. Now I'd like to show you what I mean by that. So I'm going to use these ping pong balls to represent electrons flowing through a circuit. Instead of electrons going to a device, my ping pong balls will be delivered to the chalkboard, and they'll be doing work on the chalkboard, making tiny little dents in it that we can hear the noise of that being made. So if I'm going to claim that current, how fast charge moves through a circuit, affects power, how fast work is done, I have to justify that somehow. I think it's pretty easy to see with ping pong balls. If I throw the balls infrequently, work's not getting done very fast. There's not much flow of ping pong ball, and so any change to the board is happening very slowly. Contrast that to if I start throwing frequently. Change is happening pretty quickly because the balls are hitting the board much more often. So clearly the frequency at which I throw the ping pong balls is very important. So we just justified how power, joules per second, must be proportional to current, coulombs per second. The more frequently charge reaches its destination, the faster work is being done. But this is not an equal sign. If we wanted to turn this into an equation, we would have to say something like power equals current times some constant. And what would the units be on that constant? Well, let's look. We've got joules per second for power. We've got coulombs per second for current. So if we wanted these to be equal, the units on our constant have to be, well, on top I have joules here and coulombs here. So I must put joules there so I can get joules on top somehow. Now, it turns out I don't want coulombs on top, which I'd have here. So to get rid of them, I have to put that on the bottom. So if I have this unit joules per coulomb, then coulombs cancels, and I end up with power. So obviously we've seen that unit joule per coulomb before. That's the volt. So this constant here must actually be the electric potential. We need to now justify why the joule per coulomb, the electric potential, should have anything to do with power. I'll use the ping pong balls again. You know that how frequently I throw the ping pong balls, the ping pong ball current representing the electric current, affects how quickly the board gets energy. But what else matters? How hard I throw them. In other words, how much energy does each ping pong ball get? So if I do kind of a wimpy shot at a certain frequency, I'm not giving the board that much power. But what if at the same frequency I really winged the ball? Whoa, didn't expect that. If I really throw the ball fast, each individual charge hitting the board is going to have more of an effect. And that's the energy per charge. That's the potential, the voltage. So those two things together, how frequently does a charge arrive and how much energy does each individual charge have, that's what's important in determining how quickly a device uses energy. We'll pick up and use this equation in future lessons. For now, I want to take one more look at the light bulbs and 9-volt battery we were looking at before. And I want to look at how power in an electric circuit compares to the mechanical power we've seen up till now. Did one other calculation to try to put the amount of energy we used in those 10 seconds in perspective. I recognize this is a 9-volt battery, which means each coulomb got 9 joules. Since we had 1 coulomb, we got 9 joules total. And I thought we would take a look at that in terms of potential energy. How high would I have to lift this 100-gram mass in order to get 9 joules? And it turns out not very high, 0.9. All right, so my battery's running. You can see the light bulbs lit up, and it is outputting 9 joules every 10 seconds. And I'm going to do the same thing. I'm going to give this little weight 9 joules of potential energy, and I'll take exactly the same time, 10 seconds. So we'll both be giving it the same energy with the same power. So we're both, I guess, 0.9 watts. So here we go. Starting now. There we go. That's 9 joules in 10 seconds for both me and the battery.